In this recording, we discuss whether interference is going to happen from a single slit, what we call single slit interference, or what we usually more often call as diffraction. Think of a slit just somewhat like this. Now, if I have a light beam coming in, a light wave coming in, once it's going to come in contact with the slit, now each of the ends of the slit is going to be able to bend that light, and each of these ends is going to act as a source of light that way itself. Now, in theory, because of that, we should be able to get constructive interference and destructive interference fringes on a screen far away from the single slit. Now, just to recapitulate, if there was no diffraction, the bending of light through the edges, then when we shine light on a slit, we should just get a shadow of that slit. Now, because of diffraction, because of the interference of the light due to both ends of the slit, we should be able to see fringes like this, where we have a maximum and then some dark fringes, or what we call minima. So some maxima and some minima. Now, excuse me, let's try to explain that a little bit. Now, if I have a light beam that's coming in from the top of the slit, once it's going to get to the screen way out there, far away from the slit, and let's consider other light beams, like this one here, that's coming from half a wavelength. Not half a wavelength, half of the slit width away. Now, if the path difference between these two beams is equal to lambda over 2, then ray 1 and ray 1 prime are going to add up destructively. But then the interesting part is, if we consider just another beam just below that one, and then consider another beam, 2 prime, that's coming from the same distance a over 2 below. The path difference between 2 and 2 prime is going to still be a over 2 sine theta equal to lambda over 2. So the two beams are going to are going to add up destructively as well. They are going to destruct. Think about this. Think of this for all possible beams. This and this. This and this. As long as we have a over 2 difference between them. Which is telling us that all the beams from the top are going to interfere destructively with the beams from the bottom, getting what we call destructive interference. So every beam originating at the top half is going to interfere destructively with the beams originating at the bottom. So we get destructive interference, or a minimum. Now, what would that minimum be given by? If you look at the equation here, the half cancels out, and that gives us sine of theta is equal to lambda over a. That reminds us very much with the equation I sine theta is equal to lambda. Now, a here is the width of the slit. Theta is the angular position of the first minimum, and you understand what lambda is. Now, the equation, in general, can write it like we wrote the other equation. Notice the difference. Instead of d, we have a, and n gives us the different orders. However, this formula is giving us the position for the minima, the positions where we have destructive interference, not constructive interference. Now, like in the other case, look at what's playing a role here, A, which means the bigger A, the smaller theta, or the smaller the position of the minima, the smaller the width of the minima, and then the larger the lambda, the broader the pattern. Okay. This happens, diffraction happens only when the width size is larger than the wavelength. Okay. This is the way it's going to look. For example, here we have, this is the position of our first maximum, and this is the position of our first maximum from the other side. Now notice how different this is from the interference pattern from two slits. The central maximum is wider than the other maximum. It's actually, in this case, twice as wide. Now, we have a bright central maximum. These are the position of the maxima, the minima given by the equation that we just had. A sine theta n is equal to n lambda. So this would be for n equal 1, n equal 2, n equal 3, n equal 1, 2, 3. Now, if we were using white light, we are going to have a bright central maximum, and then at the middle it's going to be white, but the width is determined by lambda, so blue is going to be thinner, so the edges are going to be red, and then we get the pattern we should expect from this. Okay, let's play a little bit with WebTop, the same simulation we have used before, but here we have it set at one slit. Notice here, when I'm going to change the wavelength, if I increase the wavelength, let me increase it manually, so 600, 650, 700. So you notice the larger the wavelength, the broader is the pattern. And this is our central maximum. This is the first minimum. This is the second minimum. The third minimum is here. You can see it from the other side. This is the minimum for n equal 1, the minimum for n equal 2, the minimum for n equal 3. Way here, we see only one minimum. Now, if let me decrease the wavelength again. Let's go here to 500. Okay, you see it getting narrower. 450 and 400. See it getting narrower. Now, what I'm going to change is the slit width. I'll change it graphically here. If I make it narrower, it becomes wider. The pattern becomes wider. If I make it wider, the pattern becomes narrower. Now the key thing here, when we looked at two slit interference, let's put two slits here. Notice here, two slits. Look at what we have here. And one slit. Two slits and one slit. So actually, in this screen, we have two things happening at the same time. The interference pattern due to the two slits, and we are not seeing them very well here, and the diffraction pattern due to the one slit. These are the interference fringes. And these, the big ones, are the diffraction fringes. Okay, let's go for a smaller slit width. Okay, you notice here, this is an interference fringe, another interference fringe, but we don't see the interference fringe here because it coincides with the first diffraction minimum. Let's see that. There's the diffraction minimum. Okay, let's put it back. It does not want to go back. Okay, I'll stop it there. This is misbehaving right now, so I'll stop it now. Now, that was the discussion of slits. What's going to happen if we have, instead of slits, if we have holes? Like here we have a circular hole of diameter d, what we call a circular aperture. Now, it's going to be the same idea, but there is a slight change due to the geometry. So actually, if d is the diameter of the hole, of the aperture, it's going to be d sine theta is equal, instead of 1 lambda, it's going to be 122 lambda. There is that factor 1.22, that's due to the geometry. So that's the position of the first minimum. And then you have the other minima as you go on. Let's try to pull out something from WebTop that shows that. Hopefully it will show it. Okay, this is what's called the circular aperture. Okay, what we are seeing here is a little bit more complicated, but you see it there. So I moved it a little bit further away. Okay, let's look at it. So we have an interference pattern. That's the middle point. This is more complicated interference. This is for when the screen is close to the aperture, but we're not going to get into that, just to speak of the full idea. And I purposely went to the simulation to show you something else. What if instead of an aperture, instead of a hole, we have an obstacle? Meaning it is open on this side, and then we have a circular thing blocking it. Okay, now in that case, you see we have actually an interference pattern. Light is going to bend from the edges, resulting in an interference pattern with constructive interference in the middle, as we see it here. Now, a few more questions before we finish. Now, actually, let me say one thing. If we have that aperture that we block the light with, think of it as just like a penny that you put in the path of a wide laser beam. What's interesting, if you shine the wide laser beam on that penny, as a reflection of that penny, in the middle of it, you are going to see a bright point, like we saw it in the simulation a little minute ago. And that's because light from all the edges is going to travel the same distance to get to the middle. It's going to bend through the edges of the penny and is going to travel the same distance to result in constructive interference. Okay, let's answer this question. We shine a laser at a screen through a very small hole. If you make the hole even smaller, the spot on the screen is going to get larger or smaller. Okay, remember the equation for a hole. It's sine theta is 1.22 lambda over d, the diameter of the hole. So if we make the hole smaller, that's making d smaller. D smaller, but it's in the denominator, that makes theta larger. So it should get larger. Which will depict the pattern on the screen more correctly. It is number 3. Why is it number 3? Because it gives us a bright spot in the middle. That's where we have constructive interference. This is where I'm going to have my first minimum, constructive interference again, second minimum, and so on. This one gives us destructive interference in the middle, which is not correct. And we should have interference, and that's why it should be that way. Now, there is an interesting application of this phenomenon, of the phenomenon of diffraction. What, for example, if you are trying to look in the sky at two stars that are very far away, when are you going to be able to resolve these two stars and determine that you have actually two stars as opposed to one? Now, the criterion for resolving two different light sources is when the minimum of one will coincide with the central maximum of the second one. The first minimum of one will coincide with the central maximum of the other one. Let's use WebTop again to look at this. Here is, we have a Rayleigh Criterion simulation. Okay, so here we have our two sources far away, and we say that it's barely resolved when, look at your both sources. This is the minimum of one, that's the minimum of the other one. So it is barely resolved when the maximum of the second is going to coincide with the minimum of the other one. That's the Rayleigh criterion. Now, of course, it's going to depend on the size of the hole. You see, as I make the aperture larger, they become more resolved. If I make it smaller, they become less resolved. Now, it's going to also depend on the wavelength of the light. Now, as I change the wavelength, if I increase it, you notice they become less resolved. As I decrease it, they become more resolved. Let's take this example. Astronaut Joe is standing on a distant planet with binary suns. He wants to see them, but knows that it is dangerous to look straight at them. So he decides to build a pinhole camera by poking a hole in a card. Light from both suns shines through the hole onto the second card. But when the camera is built, astronaut Joe can only see one spot on the second card. To see the two suns clearly, should he make the pinhole larger or smaller? Should he make the pinhole larger or smaller? Okay, this is what we just have discussed. Actually, let me pull it up again. So what happened for Joe here? Let's see. So he sees both stars as one dot. To get them resolved, should he make the hole larger or smaller? Larger or smaller? Okay, now this one here, we should be able to see the intensity. You see it's much more resolved when we get larger. So he should make the pinhole. Now this is another question. How does the maximum resolving power of your eye change when the brightness of the room is decreased? Now the brightness of the room is decreased. When the brightness decreased, what happens? Your pupil your iris is going to open up, making your pupil larger. Now if your pupil is larger, that means our D is larger. That means the position of the first minimum is going to become closer to the middle. So what happens to the resolving power? It increases.